Hello and welcome back. So, in the last class we had started talking about particle image velocimetry. We contrasted it with particle tracking velocimetry. Today we are going to learn more about particle image velocimetry, but there is one specific issue about the lighting and the light sheet calculations that we wanted to discuss. So, where we left off last class is where we discussed this particular problem of multiple lenses put together, and we can see here this equation we discussed again. So, this equation was stated without proof, this where we have two lenses with focal lengths f1 and f2 put to, separated by a distance of d, and this equation here which tells us the image distance from the second lens that was stated last time. We will see how this applies to light sheet optics in particular, and we discussed that. So, in preparation for that we discussed what happens when a collimated beam of light enters from the left. So, a collimated beam of light is basically a set of parallel rays that will come in from the left and enter the first lens and then be transmitted through it and then again encounter the second lens and finally form an image. So, in order to accommodate a collimated lens, a collimated beam of light, we assume that S01 tends to infinity, and subsequently when we used this limit, we got this particular form of the back focal plane. Okay. This is an important equation because we are going to use it today. Okay. And we also discussed one more simplification which I will not use so much, but it is applicable in many cases. What happens when the lenses are really close, which means the limiting case of d tending to 0. So, this equation, the back focal plane equation, simplifies further and becomes this particular equation. Now, in order to put this understanding to test, we wanted to do one sample problem. In the sample problem, we had said that there are two lenses next to each other. There is the first which is a spherical lens and the second which is a cylindrical lens. Because the cylindrical lens, the optical axis is not the axis of symmetry, hence the diagrams in the side and the top views now start to differ. So, while the spherical lens remains a spherical lens in the top and the side view, the cylindrical lens does not, right. And in this in this diagram, what we have done is in the side view we have drawn the cylindrical portion, and in the top view it is just like a flat rectangular slab. Consistent with our discussion on collimated light, we said that there is a beam that is entering from the side, and in this beam, let us say this beam diameter is provided to you as d laser as 2 millimeters. Okay. And this light enters from the left hand side, encounters the first lens, goes on and meets the second lens, and then the question was to figure out where the back focal plane is and some of the other characteristics as to the experimental section which you would want to design in a given situation like this. So, I hope you have taken a look at this problem and tried to solve it. I will go through the solution portion of it today, and I will explain these things in detail. Okay. So, let us see. So, now before I start off with the solution, one thing I would like to point out, and Abhinit was good enough to point out to me last time, is that this diagram is severely exaggerated. So, the diagram in the bottom, if you see the distance I am giving it as d as equal to 10 millimeters, whereas I am saying that the focal length of the first spherical lens is 500 mm, which means that in the top view the collimated lens rays come and they get focused, right, 500 mm from the first lens, because the second lens is just a rectangular slab, it does not affect the convergence of these light rays. So, this distance is going to be 500 mm. So, this is not to scale, and this is a highly exaggerated image. So, so let's make sure that we have that into account. Now, this location is the back focal plane, and this is where because of the nature of the two lenses, the light rays come and become focused here onto a spot. We will discuss the issue of the spot little bit later, but in geometrical optics these two rays will come and meet at a point. Okay. So, this entire collimated parallel rays are supposed to come and meet at a single point here. Now, this is the area where in practical reality you have the minimum laser waste. So, you have the minimum laser waste at this location. And this is the ideal location for your experimental test section. For experimental. Right. So, what is the formula for the back focal plane in the top view? That is nothing but f1 minus d, right. So, this is 490 mm, which means that the back focal plane is placed at a distance of 490 mm from the second lens. Right. But what is the back focal plane with respect to the side view? So, back focal plane for the side view we still have to calculate. So, let us see what the formula said. So, the formula was f2 d1 minus f1 and d minus f1 plus f2. Okay. So, let us write this down. We have f2 d minus f1 d minus f1 plus f2. So, and the values have already been provided to us. So, let us just go ahead and use those values. f2 is minus 25 and this is 10 minus 500 and this is again 10 minus 500 minus 25, okay, and this is in mm. And if you calculate this comes out to be approximately minus 26 mm. You can double check my calculations, please do so. Which means if we are to interpret this in this above diagram, what this means is that these rays actually form a virtual image at a distance of minus 26 centimeters millimeters from the second lens, right. So, so this is how the, so now if I were to combine these two into one image, both these diagrams. So, let me draw just a second. I am going to draw the two drawings together, but instead what I am doing is I am drawing, I cannot draw both the, let me just finish the drawing here, then I will explain what I am doing. Okay. So, this two rays meet here. I will use another color to demarcate the other view. So, the red colored line they depict the side view for the light, and the blue colored one depicts the top view for the light, right. So, they come and here. So, you can see that the I cannot draw both cross sections for the lenses simultaneously. So, I will just keep it at that, and at this location there must be a height. So, this is, if this is the back focal plane, there is a certain span of this laser light sheet, and the other question is to find out this particular span if this D laser is already given to you. So, this D laser is given to us, right. So, this diameter is given to us, And then the question is to find this h. Now I'm going to take an advantage here of the fact that the distance between the lenses is much smaller than this particular distance. This is 490 mm and this is just about 10 mm. So the diameter of the laser collimated beams here is approximately the same as the diameter that you will encounter at the second lens. So this diameter that the second lens sees, this is dl dash. This dl dash is less than dl, but I'm going to assume that because of the small separation, I'll go ahead and assume that dl and dl dash are the same. Okay. Now in order to find out what this h is, I apply the idea of similar triangles. This is geometric optics. So geometry is basically the determining factor in everything. So here one triangle is this small triangle right here, and so apply similar triangles, and then you have dl dash by the back focal plane BFL. Just a second, I just want to make sure the side, yeah, BFL side is equal to h by the absolute values of BFL's side. So h divided by this total distance, which is this negative distance here and this positive distance 490, right. So my h here you can calculate. So my this is known to you as so h is nothing but 2 divided by 26 multiplied by 490 plus 26. Okay. So this in mm, and this comes out to be something around 40 mm. Okay. Again, you should double check my numbers. There's always a possibility that there might be a small error. So now you are going to place your experimental section here, and your h is 40 mm, which means that your experimental cross section, test section, must not have a span greater than 40 mm. Right? In reality, actually, the experimental section must be even smaller than, much smaller. I'll tell you the reason for that also in a minute or so. But your experimental cross sections should be something like this, which is placed at the location of the back focal plane, and its span should be much smaller than this h, right? Which is why we had to find the value of h. So you know how to create your experimental cross section. Okay. So now we have been discussing the entire problem from the perspective of geometrical optics, and as I said, this entire calculation above, it takes into account certain idealizations of geometric optics, which is that this collimated beam of light is actually going to come and become a single point and converge onto a single point here, but that doesn't happen. So geometric, so let's write this down. So geometric optics predicts that light sheet thickness at the back focal plane is 0. Right? This does not occur in reality. For two reasons. One being diffraction of light. So at these very small length scales, how light is being bent has to be understood through the perspective of light diffraction, and that says that light cannot be focused onto a ideal point. Instead, the diffraction results into spot size, a finite spot size, which is usually of the order of the wavelength of light being used. Okay. The exact calculations I am not presenting, it is not exactly lambda, but it is of the order of lambda. So, so we have to take diffraction into account, and the other portion is that in most cases the laser is formed in a laser cavity, and in laser cavity there would be mirrors which result in a finite beam waste of the mirror of the laser, and because of the finite beam waste it cannot be the laser is cannot be focused onto a single point. So, the other reason is that the beam waste is caused by curved mirrors in the laser cavity, and because of this beam waste the laser is focused onto a point, and this is usually the size of the point usually results in a spot size greater than lambda. Okay. So, this is something to take into account. Again, I am not, this is not a course in optics, but if you were to take a course into geometric optics, you might encounter all the correct formulas and the correct methodology for calculating all those. So, we are unable to go into all that, but I encourage you, I have already given you the correct references, so you can take a look at those. Now, these are not the only issues that an experimentalist should be cognizant of. There are other issues as well. And one of the most important issue is the fact that the laser intensity. Okay. So, going back to this particular problem, if you were to take a cut at any given location, let us say here, right. So, if this is a cut at this cross section, the laser intensity is not the same at this cross section, at this, let us say the edge of this cross section versus the middle and versus any other point in between. And that happens because the lasers do have a spread in intensity. Now, so let me write this down, please. So, there are other issues that an experimentalist should be aware of. And the example is that in most lasers, the fundamental let me rephrase this. The fundamental mode of operation of a laser, also called the TEM00 mode, transverse electromagnetic modes, TEM00 mode, the laser in the most fundamental. Okay, so this is in the most fundamental mode of the laser has a Gaussian profile, Gaussian intensity profile, which means that if you were to draw a diagram, and this is, let us say, R, which is the R of the radial distance. So, so going back to this, if you were to use R in this direction with this being 0, the origin, then if you were to plot the intensity of the laser, so if you were to plot this is the intensity values, then it would look something like this, okay, like a Gaussian curve, right. So, your IR is given by some I naught by root over of 2 pi sigma e to the power minus r square by 2 sigma square, and this sigma value, this is usually specified by the manufacturer. and usually the laser is cut off at a physically cut off at either sigma or 2 sigma. So you should find out from the laser manufacturer what the intensity distribution is. The values are usually given by them. So if that is the case, that means that in this, if we go back to this particular problem, the intensity is the lowest at the edges, right. So intensity is lowest here. So here it is basically the intensity is probably going to look something like this, and the intensity is the greatest along the center line, and that intensity is going to be reflected right back again here, right. So at this cross section. So again, okay, I'm running out of space here, but if I were to just extend this line somehow, and you'd have a very similar profile for the laser, which means that the light intensity at these edges, right, this edge and this edge right here, they would be the lowest, whereas along the center line, the mid section of the of this laser sheet, your light intensity would be the maximum. So as a good experimentalist, you should choose the middle section. Maybe half of this H would be a good rule of thumb, and that would allow you to illuminate your particles properly. Okay, so we were talking about light sheet optics, right? And the reason for light sheet optics we also discussed is that in macro PIV, you want to illuminate a large section, and you have a laser that can be sculpted into a laser sheet, and that allows you imaging without much issues. Now, if we were to go back to just one second here, I'm just quickly going to try and find this video here. So I am going to quickly explain this situation. Now, this situation here, in this particular video that I hope you recall, I'll play this one more time. Okay, so this situation is that there is a box here, and the box is filled with particles everywhere in the entire volume. So if you are watching from the side, if you have, this is where your camera is, you are going to see all these particles all across this span, right. So let's call this, let's say delta x or something. But you do not want to see this entire volume of particles, because you want to look at a particular plane, most likely the focal plane, and just that. So here what happens is, as the laser comes in and then encounters a cylindrical lens, I'm not drawing the lens, it fans out and becomes a laser sheet, and only illuminates a small distance, small gap along the focal plane, and that's how you can image a particular focal plane without having to see the particles that are far away from the focal plane. So it makes sure that you encounter a very small or a very low noise due to particles that are out of the focal plane. Now, in micro PIV, that does not happen. So what happens is, in micro PIV, so this is for micro particle image velocimetry, you have, let's say, a laser here that is now going to come through a diffuser. So there are there will be a diffuser element here, and some lenses, diffusers and lenses. I'll explain what they are for, and then they come in and go through your lens into and illuminate your sample. Now this light, if I were to use the green light line here, this green is going to illuminate this entire volume over here, and there is no way for you to prevent the illumination of this entire volume. So in micro PIV, you have so this green light that we have drawn here floods this entire volume. And because of this, you end up having volume illumination. So micro PIV has volume illumination instead of light sheet illumination. Okay. And this is a very important characteristic of what happens when you are doing particle image velocimetry for microfluidics. You have placed it onto an optical microscope, and because of the features of the optical microscope and the small length scales involved, you can no longer form a sheet. So instead, the way the laser light comes in, you actually end up illuminating the entire volume. That does lead to a little bit of an issue in the sense of you have very high signal to noise ratios, very low signal to noise ratios compared to the other cases. And if we recall one of the previous videos, just a second, I'm just going to open. So if you recall this particular video, you see that there are a lot of, so you can see that there's a particle here, for example, which is a nice finely shaped dot, whereas there's a particle here, right here, which is a big large shape. And this particle is actually, there are many particles like that, and those particles are actually out of the focal plane. There is one more particle right here, there's another particle here. These are particles that are far away from the focal plane and yet contribute to the signal in the focal plane. So you have particles which are in the focal plane, they are sharp and easily visible, and looks like a nice little circle, but the others which have this large ring like structure, they are away from the focal plane but still contribute to the signal in the focal plane. So this is an issue that micro PIV faces, and special considerations sometimes have to be put for getting high signal to noise ratios in that case. Okay. Now, one more thing is this lasers that we discussed. These are the typical micro PIV. Okay, so in a laser operation for PIV, for fast flows, PIV usually requires a double pulse laser, and we will see why that is the case, but I am just stating the issues here. For slow flows, on the other hand, and slow is obviously a relative term, and you have to watch out for what is slow in your particular case. In a continuous wave lasers, also called CW lasers, can be used. Okay. So if you are planning to set up an experimental setup, you have to be careful in selecting the laser because it depends on the kind of flow. In micro PIV, a diffuser element, which is an optical element, a diffuser is often placed in the path of the laser to reduce the coherent nature of the laser, thus preventing unwanted interference patterns. Okay. And then finally, in conventional PIV, task is often to trigger laser pulses and camera shutters simultaneously. And this can be done through the use of a synchronizer. Briefly, what a synchronizer does is it ensures that the images and the laser pulses, they are done, they are taken, they are, the lasers and the laser pulses and the imaging is synchronized. And usually what happens in a synchronizer is that control signals are generated. So this is a diagram which shows what schematically what happens. So for example, if you have a synchronizer, what it will do is, in this particular schematic, you have 3 control signals that are being generated by the by the synchronizer. So these are control signals generated from a synchronizer. Once they are generated, what happens, it triggers a laser pulse. So you can see that the beginning of the laser pulse happens when the first signal is the signal is triggered. So this, once the signal is triggered, which is basically some voltage that is usually given, you have the laser and the laser operates. Once the laser operates, then the camera is instructed to take one image. So for example, this is one particular image that the camera takes during, if it's this is an example of a double pulse laser. So you have the first laser pulse being operated, and the camera takes one frame. Then there is a certain dead time. Dead time is, so this is a dead time in the camera, and this dead time is used to distinguish the first exposure from the second exposure. So after the dead time, the second exposure takes place, so the second image is recorded. And in this particular case, this is, for example, the second signal, and the laser is again activated when the second signal is starts. So this is the second laser pulse that has been emitted, and the camera takes one more image during this. And so this becomes one full period, and this keeps on repeating again and again and again, as long as you need to have keep on taking images. And you can see that the nature of this image is that these two need not be of the same duration. It can be, it need not be. Okay, so this no. So with that, we had shown you this particular conceptual diagram last time, and we had said that there are so many different elements of PIV operation, including the light source, including the sensor operation, optical elements. And hopefully we have discussed quite a bit on the tracers. We have discussed a bit on the quite a bit on the light source, some issues of light sheet optics versus micro PIV in the optical elements, and we also discussed a bit about the sensor triggering and how 2 images are taken. So right now, so we'll stop here today, and in the next class we will get to see aspects of this image processing that are very, very important part of particle image velocimetry, right? So we'll stop here today, and I will see you next time. Thank you.